There we go. It says we're live. Excellent. Cool. Today is the calculus AP exam, right? Okay. Oh, well. All right. Some people are nodding yes. Yeah. I'm assuming that. It says for the people online, I have like at least 3 or 4 people who are taking the calc AP exam. I don't know, but yeah, we got a few more weeks. As I was talking with Mr. Geddes, I'm going to be proctoring some science exam tomorrow. I can't remember. Wait, no, it's not. Is it science? Maybe it's English. I don't know. They're dumb subjects. But I'm going to be proctoring something tomorrow. But obviously that doesn't affect you. I just thought I'd point that out because it's whatever. Anyway, well, that's the way it goes. So, like I said, for those that are here, I wanted the Chromebooks open because I wanted to be able to use the calculator for the first part of today's class. Basically, here's the rundown. I want to finish up the problem that we were doing last class, the one with chi-squared testing. I want to show you how to perform certain tests in the calculator, especially if your calculator ends up not having that particular test. I'll talk about those details in a little bit. I have some other things that I want to talk about with chi-squared testing. Question: have you ever used matrices on those calculators? Okay, I'm going to show you something today. This is going to be great. Matrices are typically a part of the Algebra 2 curriculum. They're not typically a part of anything else, but we'll get into those details today. And then with whatever time we have left, I want to continue reviewing that multiple choice quizzes. We left off on number 8, or we finished up number 8 or something along those lines. But I wanted to make sure that we at least continued with some of those, because some of those questions obviously kicked our butt last week. But we'll figure that stuff out. So anyway, I'm going to point out my bow tie because my wife made it for me. It's just acceptable for today. If you don't understand why it's acceptable for today, we cannot be friends. Okay, thank you. All right. It's May 4th. Thank you. Yes. Okay, cool. Great. Anyway, for those in the live chat, if you would be so kind as to leave a comment, that would be absolutely wonderful. And we'll get started with that calculator usage. Let me just get this thing set up right here. Why is that so dark in there? Oh, there it goes. Good. Okay. So last time we were dealing with a problem with chi-squared. I'm trying to see where I wrote my notes for that. I hope they're in here. Yay, chi-squared. So let's see what we got here. We were talking about the traits of earlobes, whether or not they were attached or free, and whether or not you could roll your tongue. I told my wife about it, and she immediately asked my son to try and roll his tongue, to which we found out that he can't, and he just simply sticks his tongue out straight. It was quite adorable, especially when he kept trying. But the idea, and I'm just kind of, these notes you already have, I'm just kind of recapping what we did last time so that I can introduce what we're doing this time with it. But I introduced this idea of the ratio of 1 to 3 to 3 to 9. Basically being that of these 4 particular categories, whether or not you can curl your tongue, whether or not your ears are attached or free, they typically occur in the ratio of 1 to 3 to 3 to 9 in any general population, or that's the genetic theory. So if a class has 124 people, we were able to figure out the expected number of people within that class that would fall into each category. But then the teacher of that class actually did the observed accounts, the reality of the situation. And the question then became, if I could slide this up right here, how closely do the observed numbers fit the expected model or the null model? Or do the observed numbers fit the null model close enough? And I walked you through the rationale behind it, and eventually we got to this idea of chi-squared testing. We went through the assumptions and conditions. And the last bit of notes that I have right here, we didn't actually write it down, but this is how they actually calculate the chi-squared test statistic. Now, we are going to be using chi-squared in the calculator because this is a chi-squared goodness of fit test. And on the graphing calculator that you guys have open, obviously you can confirm this for me, but if you hit stat and you go over to tests, scroll down a bit or scroll up or what have you, you guys have two different chi-squared tests. Is that correct? Yes. You have the regular chi-squared test up here, and you have the chi-squared goodness of fit test. Now, the problem that we were working on with the genetic theory is a goodness of fit test. You are comparing observed accounts versus a theoretical model. That is a goodness of fit test. And I'm going to have those details written out in terms of comparing the different tests together. You cannot use this regular chi-squared test for this problem. You can't. I've tried it. It won't work. If you try it, boom, it'll ask you to do the whole matrices thing, which I did. I tried with the matrices, but then when I tried to actually calculate it with the matrices, it said domain error. Like, oh, snap. Guess I can't do it. I tried it a few different ways. It got some numbers. It weren't the numbers that I wanted because this chi-square test is not a goodness of fit test. But let me go back a little bit. Stat, tests. I'll leave that up there. Let me go here. On May 25th, when you actually take your stat test, I'm still working on what calculators you guys are going to have. I need to make sure that we have enough calculators. I need to make sure that if you can't provide your own calculator, then you need to have a handheld thingy with fresh batteries or whatnot. But most of the calculators that we have in the school are these dinky TI-83s, which, by the way, yours are 84s on the computer, right? Cool. Watch this. And I showed you this last time. I'll show you it again. Stat. Go over to tests. You go to the chi-squared stuff. Oh, no. There's only a chi-squared test there. There's not a goodness of fit test. Oh, no. What does one do? Well, unfortunately, if you don't have a goodness of fit test on the calculator, you're going to have to basically do this calculation with this formula right here. And you're going to have to do it within the lists on the calculator. That's kind of what I want to walk you through here today in order to get our test statistic and then to eventually get our p-value. So this is what I want to focus on. On your calculators, everybody hit stat and edit, get to that list. And we're going to be entering in some data. I want to be entering in, let's see, let's enter in 12, 22, 31, 59. Those are my observed accounts. Or counts. Those are my observed counts. Wonderful. In the next column, I'm going to be typing in 7.75, 23.25, 23.25, and 69.75. That's a 6, 5. There we go. Those are my expected counts. That's the data that we copied down last class. We copied it down last Friday. Those are the observed accounts from that science class. I think it was a physics, no, it was a biology class, whatever. And the second column represents the expected values based on the genetic theory of 1 to 3 to 3 to 9. So now we need to use these lists with this formula. We need to do these calculations. Now, observed, that is L1. Expected is in L2. And obviously expected is in L2. So in your calculator, you need to make sure you know how to do this. Go up and highlight L3 like that. Parentheses. Now I need to get L1 in there, so I'm going to hit second L1 minus second L2, my expected counts. Close those parentheses. square it and divide it by L2, my expected counts. You need to make sure you know how to type that in, highlighting up L3, of course, because then if you do this correctly, when you hit enter, it should automatically populate list 3. Those are the numbers that should pop up if you did this thing correctly. Now, it's not important to write those particular numbers down. That's not what we're kind of focusing on right now. What we're focusing on is we're trying to get the test statistic. We're trying to get the chi-squared score, for the lack of a better term, like a z-score or a t-score. We're trying to get the chi-squared test statistic. What I need to do next, according to the formula, after I have taken care of that fraction, I need to add up all of those numbers. Now, you could do that by hand if you wanted to. I don't know why you would, but, you know, because obviously we only have 4 categories. What if you had like 15 categories? So instead, I'm going to do something like this. If you hit second stat, and you tab over to math, you have the option to get a sum. Now, the calculator can be a little bit dicey depending on what the previous screen was. So let me see if this works, and then I'll explain. If it doesn't work, I'll explain why. Yep, it didn't work. And I'll tell you exactly why. Let me ask you a question. In the past, when you use these graphing calculators, I know this happens to you. Sometimes you get to a screen that you don't know how to get out of because every time you hit clear, it doesn't go away. I think everyone's kind of mode at that point. You pretty much hit like graph and then clear. Yeah, that's what a lot of people do. You know you do it. Can't do that here. So the thing is, I just got rid of that number. Oh no, I hit the word summon. Oh no, everything's falling apart. Oh no. Can I clear that out? Okay, good, the number's there. See, the thing is, I can't go to that sum feature if I'm stuck inside of here. And then if you try to hit clear, it doesn't work. I need that number to stay there, by the way, so I just hit down. I think if I hit clear and enter, it'll go away, but I don't want to do that. I need that number to stay there. Please remind me, you calculator fiends, how do I get back to the home screen without hitting clear and without hitting graph clear? You need to know this on how to get out of certain things in the calculator. Do you know how?
Second mode.
Yeah, second mode. You need to learn how to do that. That's a very important function. Quit is above the word mode. A lot of you will be hitting second mode when you take the AP test. That's a joke. I don't believe that. Although some of you may believe that. Doesn't matter. Once I'm down here, I'm going to hit second list, and it is going to bring me over to math. It's going to bring me down to sum, and I need to sum all of L3. Second 3. That is my chi-squared test statistic. This is how you can do it by hand. If you don't have a goodness of fit test on the calculator. So if you have one of these handheld calculators like this, it does exactly the same thing. I'm just going to kind of walk through this real quick. Stat, edit. I can enter in those numbers. I have these numbers over here. Let's see. I can do 12, 22, 31, 59. Boom. 7.75. Nah, it's a minus sign. 23.25. 23.25. 69.75. Go up to L3. Parentheses. L1 minus L2 squared divided by L2. It'll give me all of those numbers that I need. Second mode, second stat will bring me here, and I can sum up L3. And that'll give me the chi-squared test statistic. That test statistic is what we need if you do not have a goodness of fit test. And we will have to utilize that in a moment. Let me show you something real quick. 2019. questions. I wanted to show you the formula sheet. There you go. This is the very last formula that they give you. There you go, right at the top of the screen. It's the last formula that they give you on the formula sheet. There are 3 pages of formula sheets, and they give that to you at the very top. So you're won't have to memorize it, obviously, but it's there just in case you need it. Recognizing the chi-squared formula is somewhat easier, only because it's unique. There are not a lot of formulas that are exactly like this, but it's kind of nice. Anyway, what does one do with that chi-squared statistic? Well, I'm going to have to show you how. Ladies and gentlemen, keep your computer screens open. But if you do not already have them out, I'm going to need those notebooks out and open. Let's see. I recently rewatched The Force Awakens. And I thought to myself, it's not as bad as I originally pegged it. The Force Awakens, that is. I am an originalist when it comes to Star Wars. Although The Last Jedi is still terrible. I can see how much you all are very much like in the vein of the Star Wars world. Yes, as many of you are like, what is he even talking about? Anywho. Okay. If you have to do this by hand, if there is no GOF, goodness of fit test, on your calculator, you can still perform the test. If there is no GOF test on your calculator, you can still perform this test. It just takes a little bit of extra legwork. You need to calculate the chi-squared test statistic using those lists. Just going to write it down one more time into my notes just for the sake of argument. Write it down a little bit smaller than I did before. But you need to calculate the test statistic, which in this case, I'll write it down right here for our example because this is a continuation of the problem from before. We got chi-squared is equal to 6.638 approximately. That is the number that we got it equal to on the calculator. From there, we are going to have to calculate a chi-squared CDF. We are going to have to calculate a chi-squared CDF. Now I'm going to show you it on both calculators. On my rinky-dink 83 calculator and on the superior computer calculator, just so we're all aware as to what has to be typed in, what the syntax is for this particular problem. So let me first flip over to the calculator on the computer. I believe that you should have these exact the exact interface that we're going to be dealing with. But if you hit second vars, you can see that chi-squared CDF is your 8th option. Come on, I hit enter. There we go. Now, the options that they give you are lower, upper, and America, degrees of freedom. Now, in this particular case, we are going to be doing 6.638, comma, big number. Doesn't matter what that big number is. And then we got to have a degrees of freedom. Now, I'm going to write this down on the paper in a minute. But degrees of freedom, as I said last class, unfortunately, is not 123. It's not 123. The reason why I say 123 is because there are 124 students in the bio class. There's 124 students, but the degrees of freedom is not 123 because degrees of freedom for chi-squared is not based on the sample size. It's based on the number of categories. It's based on the number of categories. So for here, I'm going to go 6.638, comma, big number, whatever that big number is, comma, now in this case, I'm going to write a 3. And the reason why I'm writing a 3, I'm going to put it in my notes right here, degrees of freedom is equal to n minus 1. But n is number of categories. It's not the sample size for this particular type of test. It has to be the number of categories. And in this case, there are 4 categories for your tongue and your earlobes. So you got to put a 3 in there. If I go back over here and put that 3 in, it gives me my proper p-value, boom, at 0.0843 or whatever, what have you, 0.0844 if you want to round that up. Yeah, I'll probably round it up. Let me go to my rinky-dink calculator just to show you again what this thing would look like in the regular old calculator. Zooming in, zooming in. Boom. Let's see. Second vars, chi-squared CDF. I could type in that number 6.638, comma, some big number, comma, 3, because you have to put in the degrees of freedom. And obviously, it spits out the exact same p-value that I need. Let's say you do have a goodness of fit test. If you do have a goodness of fit test, you would go over to that goodness of fit test right here, where it would have L1 for observed, L2 for expected, but you got to type in 3 for degrees of freedom. America. You got to type in 3 for degrees of freedom. Calculate. And you can see it gives you the exact same p-value that we need. That's the p-value. Degrees of freedom. Salute when you say it. But that's what we get. That's the p-value that's going to determine our answer. That's the p-value that's going to shape our conclusion. The same rules apply for that p-value. The exact same rules apply as they always have. It's too large. It's greater than 0.05. I'm a fail to reject. So I got to write out my conclusion. So let's see what this thing says. It spits out a p-value of 0.0844. The conclusion that we can come to. Because 0.0844 is greater than 0.05, I fail to reject the null. There isn't enough evidence. One might argue there is some evidence, but I would argue there isn't enough evidence to suggest the genetic theory of 1 to 3 to 3 to 9 is wrong. There isn't enough evidence to suggest that the genetic theory of 1 to 3 to 3 to 9 is wrong. America. I don't know, it just sounds fun. But that's what we would have to go through with chi-squared. That's exactly what we would have to go through with chi-squared. It's very strange. Who's in trouble? Who is it? Oh, it's security. It really is security. Hold on. Mr. Marcus, room. How's it going? Okay. All right, bye-bye. Haley, you're in trouble now. All right. It's at the security desk, you said. Sure. No one's, you really think anyone's going to stop anybody? That's true. I'll just put security. C205 at 746. Is there a red thread in there? Yep. Okay. Okay. Now, like I said, I just wanted to kind of get through this whole chi-squared thing, but I have a couple of notes on chi-squared. It's going to be, okay. Which chi-squared test do I use? Question mark. I don't know how to draw a guy shrugging. If I did, that would be amazing. I think I just do this. Kind of like a smarmy. Hold on, it's got to curve a little bit more. Kind of like that. I assume he'd be shrugging. I don't know. Anyway. But the question is, which chi-squared test do I use? Because in reality, there's actually 3 different chi-squared tests. Oh, no. There's 2 main ones that you're going to be focusing on. But I'm just going to give you a brief definition of all 3, just so we have them. But there is the one that we were just working on, goodness of fit, otherwise known as GOF, goodness of fit. It compares observed counts to a theoretical model. It compares observed counts to a theoretical model. That is the goodness of fit. Goodness of fit, well, how good does it fit the theoretical model? That's just the general idea behind it. I have absolutely no idea why the TI-83 graphing calculator doesn't have a goodness of fit test on it. But like I said, you can still do it by hand if you calculate the test statistic and then run a chi-squared CDF. The second test, and this is the one where the calculator actually does have it, and this is the other reason why you need the Chromebooks, because I got to show you how to use matrices. But there is this test, otherwise known as homogeneity. If I could spell that correctly. Geneity. Geneity. I think there's an extra E in there. I'm going to sneak that E in there. I'm a math teacher. I don't have to know how to spell. Homogeneity. Now, what this one does, it compares the distribution. Oh, she's got it. It compares the distribution of observed counts among different groups. Now, I just want to again look at these 2 tests. I want to talk about the difference between these 2 tests because it is very important in terms of whether or not you need to perform a goodness of fit or whether you need to do the homogeneity. In goodness of fit, there is some theoretical model that somebody claims is true or somebody believes is true. There's some theoretical model for goodness of fit, some accepted standard that is now going to be on trial because of the observed numbers that you found. the genetic theory of earlobes to tongue rolling? Well, we think the theoretical model should be 1 to 3 to 3 to 9. Okay, well, I just found this class of 124 students, and I'm trying to compare. Oh, hello. Sorry, I didn't know they were going to show up.
Happy Teacher Appreciation.
Oh, thank you.
Thank you for all you do.
Oh, here, I'll come over. I'm sorry. Thank you so much. I appreciate that. All right.
All right, Tyler, say you have a nice day.
You too.
Thank you.
Have they set a date yet? Have they set a date yet?
He hasn't even given her the ring yet.
What?
It's been sitting at our house. He's trying to figure out how to give it to her because she's like.
You just say, here you go.
Yeah, well, he was going to do it one way. He's like, oh, please don't give it to me in a Phillies game. She can't stand the Phillies.
I got you.
I'll let you know.
Okay. Sorry, she is the mom of a student that I taught like 10 years ago, and he's engaged to a girl that I taught like 7 or 8 years ago. And I don't know. I know a lot of stories about him. She knows that I know these stories, but they're bad. They're the type of stories where it's like, yeah, you deserve to be suspended for that one. I'll tell you it off camera. Anyway, so where was I? I lost my train of thought because now I got cookies. Yeah, so there's some accepted theoretical model, and we're putting that theoretical model on trial, comparing these observed counts versus the theoretical model. That's goodness fit. Whereas in homogeneity, there is no theoretical model, there is no accepted number, but you are comparing the distribution of the observed counts that you have amongst other groups, which are also observed counts. And I want to give you that example in a moment. But first, I just want to show you real quick the title of the third test of chi-squared. There's actually 3 of them. And then we'll go back to homogeneity, and that's what we're going to be focusing on today. There is also the chi-squared test of independence. Again, America. But there's also the chi-squared test of independence. It's similar to homogeneity. It compares if 2 variables, if I can spell variables, among the same population are independent. The test of independence is trying to determine whether or not 2 variables within the same population are independent of each other. It's different from the homogeneity test. Very similar mechanics. Very, very similar mechanics. And I'm going to show you, basically, I'm going to focus on the homogeneity test today. Again, the calculator can get it done. It doesn't matter what calculator you're using. It doesn't matter if you're using the TI-83 or if you're using some fancy, like, TI-89. There is an 89 out there somewhere. I know there is. There's actually, they've made up to the 90s. But they all have the homogeneity test. They all have the basic chi-squared test with matrices. I'm going to show you how to do that. Very weird. Okay. So the example for homogeneity, and then after we do this, we can jump back to the quizzes thing that I wanted to do. I guess I do put that extra E in there. Homogeneity. Here's a little chart for you. Within a college, within a university, there are different schools of subjects that are being taught. I'm going to try and fit all of these in. There's agriculture. There's the arts and sciences, engineering, and ILR, which I don't even know, didn't even tell me what ILR was. Whatever, I'm not going to look it up now. Doesn't matter. But there are these different schools within the university. It's like, when I was in college, I was technically a part of the School of Mathematics and Science and the School of Education, or whatever. So in this particular university, they are comparing the observed numbers of the students who were a part of the agriculture school, arts and sciences, engineering, or ILR. And, well, what happened to them? What are they doing right now? Well, these students amongst these four schools are either employed, they are either in grad school, or other. You fill in the blank for other. I mean, literally. I mean, it could be anything, really. Other could be like they're in jail. Other could be unemployed. Other could be dead. Other could, I'm not, it could be anything, really. I don't even know. But top one being employed, the middle one being they're in grad school, the third one being other. Now, these are all observed counts. These are all observed counts. So I'm just going to write in these numbers. I want you to write in these numbers as well. 209, 104, 135. These are the numbers for agriculture. 209, 104, 135. Meaning, all these students who were in the College of Agriculture, well, 209 of them are employed and the rest are grad school and other. Cool, all right. Arts and Sciences, which I guess, well, technically would be mine. I don't know, whatever. There were 198, 171, and 115. In engineering, there were 177, 158, 39. In ILR, which now it's bugging me that I don't know what it stands for, 101, 33, and 16. I'm going to look it up real quick. Because it's bugging me. Now, you could take a look at this chart, and you could come to some basic conclusions. When I say basic conclusions, I mean like they're the type of conclusions that you don't really have evidence to really back it up at the moment. But you could kind of be like, well, I mean, just kind of look at it. I mean, like, for example, what can you tell me about students who are in the engineering school? You could tell me something very important about that. Like I said, I don't know what other is. Other could technically be anything. What in the world is ILR? I really want to know. The book is not telling me. What? That sounds weird. I guess it's important. The book is really not telling me, though. I guess that's cool. Social studies or social sciences or social work? Just social studies. Industrial relations. Hey, can I tell you a fun story real quick? 30 seconds. Most of you know Mr. Germano. Is that fair? So you know Mr. Germano is the athletic director. You know his personality. He was my 8th grade social studies teacher. Yes, be shocked. I need you to be shocked right now. Be shocked. He was my 8th grade social studies teacher. I kid you not. Hilarious. Anyway, back to... Why was he a social studies teacher? I don't know. I can tell you stories. My word. Anyway. Okay, back to this. Here's the big question. Here's the big question. These three on the side are what we call postgraduate activities. After you graduate, you can either get a job, you could go to grad school, or you could do something else, whatever that may be. Doesn't matter. This other could honestly be anything. This other could honestly be anything. This other might be like, You inherited a bunch of money and now you're living at home. Cool. You're rich, but you're not working. That could be other, You're living in a gutter. Okay, that could be other. I don't know. But grad school, obviously you're working towards a higher degree. Employed, you're, have a job. I guess each has their own like positives and negatives per se. Obviously, if you're employed, you're going to be, paying off your debts. If you're in grad school, hey, good for you, but you're going to be incurring more debt. Other could be anything. But here's the big question. Do the postgraduate activities among the 4 colleges have the same distribution? I want to talk about the consequences of that question. I want to talk a little bit about the nuances and the consequences of that question. But do the postgraduate activities among the 4 colleges have the same distribution? Are they the same? Depending on which college of study that you go to, if you're in the College of Agriculture versus the College of Engineering, do you have better prospects of getting a job? Or does the college that you're in, maybe it requires more grad school? I don't know. Like, I think about it, like if you want to be a doctor, pretty much you have to go to this form of grad school called medical school. If you want to be a lawyer, you have to go to this form of grad school called law school after you get your bachelor's degree. So it really depends on what you're studying will determine, well, not will determine, but it may determine what you end up doing after you graduate with your bachelor's. The thing that I was pointing out about engineering before, if you look at engineering, there's a distinct difference between the engineering students who are employed and in grad school versus other. This is a much smaller number. Whereas if you go to like the art sciences, they're a bit closer together. I don't know. Agriculture, agriculture, it looks like there's like more, like a lot of people who are employed, but also a lot of people who are other. So do the postgraduate activities have the same distribution, or is there a possibility we could reject that null hypothesis that they are all the same? And that, well, maybe it does depend on what you study in college that determines what you do after you graduate. I don't know. Craziness. It really does depend. I don't know. A lot of you guys are obviously planning for college, and a lot of you are going to college by the end of the year or whatever. I don't know. It's your prerogative. But what you end up studying could be like a super awesome thing or a super devastating thing, or this could really get me a job one day, or wow, this is really not going to get me a job one day, or I don't know. It really depends. Everything really depends on what you are going to do with it. So like, I could just go get like a general degree, but then if I have the drive to do something, I can go do something with it. Maybe it doesn't matter what I'm studying. Maybe I just need to get the degree, and then I can do whatever the heck I want to do if you have the drive to do it. But this question is not taking the human factor into it. I kind of is, but what it's really doing is saying, okay, does it matter what you're studying? That determines what you end up doing. So here's what we got to do. First and foremost, I want to show you how to enter this stuff into a matrix. And then I want to talk about how we kind of are going to be comparing these things. So go to your graphing calculators. And I need you to find the matrices, the matrix per se. Now the matrix, just for the sake of argument, I'm going to zoom in on this calculator and you can see it. Zoom in. It'll focus in a moment. There it is. If you hit on the left side of your calculator second, and then this button right here, it'll take you to that matrix. Except it's missing an I. I never noticed that till now. It's missing an I. That's cool. Anyway, on the graphing calculator, on the computer, it's the same thing. Second, and then this button, and it'll take you to this screen. On your graphing calculators, if you ever see a bracket like that with a letter in the middle, it is referring to a matrix. Just so we're both on this, or both, all on the same page. If you ever see brackets like that, they're talking about matrices. In fact, I'll get out of this real quick. If you go to the regular chi-square test, you can see observed and expected are in those brackets. They are referring to matrices. Question. In Algebra 2, or Algebra 1, doesn't matter, I don't care. Did you ever spend a lot of time solving systems of linear equations? Using substitution, using linear combination. They call it elimination, I think. Do you ever learn how to do it with matrices? Oh, sad you. Sad all of you. You can solve those with matrices. I can't teach that today. Anyway, back to this. So what you do is this. There are 3 subcategories on the top: names, math, and edit. See, the thing is, if you hit enter on the first one for name, nothing really will happen. Watch what happens. Just does that. And there's nothing in the matrix. It's undefined. Because you have to define the matrix. So what you're going to do is this. Second matrix, you're going to go over to edit. Ms. Markey, it's the exact same list. I know, but you're going to go over to edit. And when you're on edit, hit enter on the first one. And it'll take you to this screen right here. Now, right now, that is clearly a 1-by-1 matrix. The order of those numbers, 1 by 1, in order are talking about the number of rows and the number of columns. In that order, rows by columns. So for our example, I'm going to put in a 3-by-4 in that order. 3 rows and 4 columns. Type in the numbers that I just wrote down before for homogeneity, or for this homogeneity example. Just the numbers, obviously. Let's see, 209, 8, 7, 101, 104, 171, 158, 33, 135, 115, 39. It's always in the form of row by column. I'm sure at some point in your lives you guys have heard of like mathematical matrices, like heard of them maybe. Yeah. You guys don't know what these calculators are capable of. You really don't. Have I told you about the Apollo 11 thing? I never told you about the Apollo 11 thing with calculators. Okay, check this out. Now, obviously you're on a Chromebook, no big deal. Look at this calculator right here. I'll show it here. Look at this calculator right here that I have on the screen. This tiny calculator that was built in the 1990s. This was built 25 years ago, this calculator. The calculator that I'm holding has more computing power than the Apollo 11 space mission. This calculator has more computing power than all of the Apollo 11 space mission. I'm talking about the rocket that launched from Florida. I'm talking about mission control in Houston. All more right here in my hand. It's insane. If you ever watch, just for the fun of it, has anyone ever seen Apollo 13, the movie? Okay, there's a scene that I just saw recently. I don't know when the last time any of you saw it, but there's a scene in the movie where they needed to confirm calculations for something. And in order to confirm the calculations that the guys did up on the ship, all these guys in mission control, these NASA scientists, are very quickly jotting down in pencil all of these mathematical calculations with a slide rule in order to confirm that the calculation was correct. It was amazing. Watch that movie. It's great. Anyway, back to this. Click. Once you have those numbers in there, we can now perform this test. Now, just for the sake of argument, I just want to show you what this test looks like, and then we're going to backtrack to our notes. So what I'm going to do is I'm going to get out of here. I'm going to hit second mode just to be safe. Second mode to get out of that matrix because I don't want to change anything. Stat, tests, not the goodness of fit, but the regular chi-squared test. Now check this out. Observed, we typed that in. Expected, did you type in anything for expected? Nope, because you don't have to. The calculator will do it for you. What do you mean, Mr. Markey? Well, let's see what happens. Let's actually calculate this, and I will show you what the heck happened with expected matrix B. So let's go to calculate. Chapow! It does it for us. Excellent. Why are the degrees of freedom 6? I'll tell you why, don't worry. But everything is done for us. Now, put your eyes on my screen for a moment. Put your eyes on my screen for a moment. You don't have to do this. I just want you to see. Oh my gosh, look at that. Matrix B? Matrix B already has stuff in it. Yes, it does. Watch this. Matrix B, enter. Look at those numbers. You didn't type those in. The calculator did it for you. It's wonderful. Those, according to my chi-squared test, are my expected values. Where the heck did they come from? How did they do them? Well, let me go back to here. You don't have to write this down because it's not necessary. You don't have to write this down because it's not necessary at all. But I'm going to put a couple of pieces of information up on the board. But you don't have to write this down. I'm just telling you because the calculator will do it for you. I need you to recognize how it was done, though. So what they did was they figured out, okay, let's see. If I were to actually continue this table right here, there would be 685 in this category, 466 in this category, 305 in this category, and 1456 overall. They kind of figured out the rest of this two-way table. And they determined that 685, I'll put this in a different color. Put this in, I'll put in black. There we go. 685 is approximately 47% of that big number. And 466 is 32% of that big number. And 305 is approximately 20.9% of that big number. And they basically said, okay, we'll go back to the question. Do the postgraduate activities among the 4 colleges have the same distribution? So let's compare the distribution of agriculture, boom, 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 to these percentages, 47%, 32%, 20.9%, and see how the counts, the observed counts, match up against the expected. Same thing here. Arts, sciences, this is the actual distribution, this is the observed distribution, but these percentages are the expected distribution. Same thing here for engineering and ILR. Here are the observed counts, here are the expected distribution counts. The calculator does it for you. You don't have to write it out. It's kind of nice. The calculator will figure out the expected values so that you don't have to, and you don't have to waste your time actually doing that by hand. Because I want you to imagine something. I want you to imagine something. Back in the day, when they did not have these graphing calculators, you would have to create a completely separate matrix. Like, let me go here. Boom. You would have to complete that expected matrix based on all of those distributions. It would take you probably like a half an hour or more because you don't have graphing calculators. Then, once you have the expected matrix, well, I have the observed matrix, I have the expected matrix. What the heck do I have to do next? You would have to calculate all of that by hand. Observed minus expected squared over expected, and then add up every single cell just to get the test statistic. But the calculator does it for you, which is nice. Just for the sake of argument, when I ran this test, get to the chi-squared test, you can see that test statistic at the top of the screen. 93.66 is what it actually ends up being. It's kind of nice. Let's actually run through this a little bit. I got to give you some assumptions and conditions and degrees of freedom. Come on, paper. Do your magic. So this is the homogeneity test. First of all, a null hypothesis, just something very simple. The 4 colleges have the same distribution. My alternate hypothesis, the 4 colleges don't have the same distribution. Again, the null hypothesis being nothing to see here, nothing going on, nothing out of the ordinary. They all have the same thing, no big deal, no difference between them. That's the null hypothesis. You got to write it out in words, unfortunately. And then the alternate is, well, no, they don't have the same distribution. Okay, all right, see what happens. Assumptions and conditions. They're exactly the same. It's literally exactly the same as the other chi-squared test. In fact, I'm just going to write that. Exactly the same as GOF test. It's exactly the same as the GOF test. You have to have counted data, randomness in selecting these people, which, yes, it was assumed based on the question that I read. Independence amongst the, you could say independence amongst the college that the student went into, or independence among the decisions made postgraduate. 10% condition obviously has to be hit. And the expected cell count, the expected count in each cell has to be greater than or equal to 5. And if you go to the actual matrix for matrix B, you can see that every single one of these cells is greater than 5. So the expected counts work. Yay. It's exactly the same. I just didn't want to have to write all of those out, because I got those other things I want to get to. So it calculated the test. I got a chi-squared test statistic of, where did it go? Come on, you thingy. To run you again. What in the heck? I did it again. Hold on. Get it. Get it. There we go. 93.66 with a p-value of approximately, holy crap, 5.3 times 10 to the negative 18. That's not us. With degrees of freedom at 6. That's what I wrote down. This p-value is essentially 0. It's essentially 0. But why are the degrees of freedom 6? Well, for homogeneity, degrees of freedom are equal to the following. Rows minus 1, columns minus 1, multiply them together. There were 3 rows. There were 4 columns. You do those calculations, it gets you 6. It's wonderful. Degrees of freedom get a little bit iffy later on with, chi-squared, obviously. Like, originally, it's just n minus 1, sample size minus 1. No, not anymore. Not anymore. With chi-squared, it's a little bit different. Has to do with the categories. Have to do with the number of categories. With a p-value so low, approximately 0, we reject the null. There is enough evidence, strong evidence, you could even say, abundant evidence. There is enough evidence to suggest the distribution of postgraduate activities are not the same. Yeah, move that up a little bit. There we go. There is a lot of evidence, but again, it's just, we can't go into that subjective kind of standard with it. We have to basically state something like this. There is enough evidence to suggest the distribution of I said postgraduate, and I never wrote the word graduate. Graduate activities are not the same. Aha. Oh, this thing. Now, chi-squared, not today, but probably on Thursday, I'm going to be giving you an opportunity to practice some of the stuff with chi-squared, just because we do need to. I will give you the heads up about the AP test. AP test, chi-squared ends up being like 2 or 3 questions. It's like 2 or 3 questions. But you need to assume that every other student in America is going to get those chi-squared questions correct. You assume that they're going to get it correct, which means you need to get it correct. You're trying to outscore them. That's what we got to do. So we're going to get practice with this on Thursday, with both of the chi-squared tests that I've given you so far, and we'll talk about test of independence if there is time. Okay. In the meantime, I have roughly 20 minutes, a little less than 20 minutes. I want to review some stuff. So in order to review that stuff, I need you to go here. I need you to jump into this. This is the multiple choice that we were working on last week on Friday. I need you to jump into that and join that code on your Chromebooks. That would be fantastic. So we can knock that thing out. And then once we get enough people in there, we'll kind of get this thing moving, and I want to go over some questions with you. Let's see what we got here. As people are signing in. It's funny, on YouTube last year, before the AP test, in the weeks leading up to the AP test, I did live YouTube streaming for practicing AP Stat. So one of the things that I did was I went through the 2012 AP Stat questions, all 40 questions, technically 39. But I went through all of those questions last year, and I had the YouTube video sitting up there. Well, lo and behold, that YouTube video in the past couple of weeks has doubled in viewership, because I'm assuming people are like trying to get all the help that they can get in preparing for the AP test. And they're doing that, and they're like, oh, they're watching my entire live stream. Good for you. I don't know. I'm not saying that you guys have to. Anything that I put on YouTube, like, for fun like that is purely optional. Well, we'll see. I may try to do some live streams. Anyway, so we already did the first 8 questions. So I actually am going to kind of try and skip past the first 8 here. So let's see what we got here. Can I actually skip it here? Sweet. So let's jump to this one. Did it jump on your computers? Sweet. Cool. Cool. Now, obviously, if you have not joined, I'm going to type this into the live stream. If you haven't joined yet, the code is 186001. I'm just putting that into the live stream just in case you want to join that thing out. And let's take a look. How do I? Oh, there it is. Full question view. There it is. So let's just go through this one at a time. A random sample of 25 households from the Mountain View School District was surveyed. In this survey, data were collected on the age of the youngest child living in each household. The histogram displayed the data collected in the survey. In which of the following intervals is the median of these data collected? Median. Obviously, you guys have dealt with median for a very long time, the middle data point. I'm just going to let you answer this one, and then let's just see what happens. Answer it up. Got 17 in there so far. Let's get that thing answered. Ooh. There. Put it on there. I got 3 more to go in there. Now, obviously, the interesting thing that they did do with this little chart here, and I think if I click this, it'll make it big. Yes, it does. They do give you the numbers at the top. And how many did they say there were? There were 25. So there were 25 students in this thing, which means that if I'm trying to get a median, there would be 12 on each side, and then the middle data point would be the 13th data point. So if you're looking for the 13th data point, 4 is here, 5, 6, 7, 5 more is 12. The middle data point has to be between 8 and 10. And you can see that right there. Boom, the number of people who picked that one. Got to pay attention to the number of data points. There are 25 data points. So you knock out the first 12 to the left, the last 12 to the right. The middle data point's got to be the 13th data point. Next question. Boom. Oh, sweet. Okay, hold on. Based on a random sample of 50 students, the 90% confidence interval for the mean amount of money that students spend on lunch at a certain high school is found to be between $3.45 and $4.15. Which of the following statements is true? I really, really hope that that this question was worded, or the answers were worded correctly. I'm going to leave you to answer this one. But I really hope it was worded correctly. We'll see. We'll see based on what you choose. Let me read through them, actually. 90% of the time, the mean amount of money. Okay, 90% of the students. Sample. 90% of all random samples. Okay, approximately. Okay, cool. 90% of all random samples of 50 students obtained at this high school will result in a nice. Okay, I'm gonna leave you to it. I just read all 5 of them, and I have an idea as to what I'm gonna do here. Yeah. So I'm still waiting on 6 more. Oop, 3 more. 2 more. 1 more. There are no more. Let's see if this thing rolls. Will it actually do it? Well, come on, click. Click. Yay, it did it. Can I actually see this? It's not going to show me the answer. Come. Oh, full question view. Got it. So the third and fourth statement look very much the same. They both started as 90% of all random samples of 50 students attained at this high school would result in A, and that's where they diverted. The third option said in a sample mean amount of money students spend on lunch between those two values. Come on, full question view. But no, it would result in an interval or a 90% confidence interval that contains the true mean. You're 90% confident that your interval contains the true mean. And what that really means is, well, if they repeated this many, many times, in this case, of all random samples of similar sample size, 90% of them would contain the true mean. You're just hoping that you're one of those 90%. It was kind of split between the two. That was interesting. Click. Question view. 10% of all Dynamite Mints candies are orange, and 45% of all Holiday Mint candies are orange. Okay? 2 independent random samples, each of size 25, are selected. One from Dynamite Mints and the other from Holiday Mints. The total number of orange candies in the 2 samples is observed. What are the expected total number of orange candies and the standard deviation of the total samples of orange candies, respectively, in the 2 samples? Interesting. What I will tell you is that when it comes to expected value, you can technically do that by hand. But when it comes to standard deviation, it may be in your best interest to utilize the lists that are on your graphing calculator. List 1 potentially being the number of trials, and list 2 being the probability of that happening. I believe on your calculators, when you run a 1var stat, there is a way to tell the 1var stat of the probability or the frequency of such a thing happening. I'll kind of leave it there and see what you guys get, and then we'll talk about how you could calculate this. Oh, that thing didn't work the way I wanted it to. What if I'm talking about the total number of in the 2 samples? Oh, I see why that is. I do see why that is. Okay, hold on. What I said about that may not be entirely true. Yeah, what I said about that wasn't entirely true. I thought it gave you other information. Interesting. Good thing this is a practice. All I have to do is read the question. All right, let me try a different calculation. You keep answering because I still got 7 more who have to answer. But let me try a different calculation here. Okay. Haha. Okay. I figured out my answer. I still got two more who have to answer. And I'm going to do it like this. There's the dynamite, and there is the holiday. 10% success, 45% success, sample size of 25, sample size of 25. So if you were to multiply n times p here, you would get, well, yeah, 25 times 0.10. Why am I even typing this in? 2.5. And then for the other one, 0.45 times 25, and you would get 11.25. And if you added the two of them together, you get 13.75. That is the expected number, n times p. I was thinking this had to do with the list, but unfortunately, the reason why it doesn't work with the list is because they didn't give you a complete distribution that added up to 100%. This is actually a binomial problem. And if you're going to calculate standard deviation is square root of NPQ. Square root of NPQ. And if you calculated the square root of NPQ for the dynamite candies, let's see, square root of NPQ, you get 1.5. And if you do the square root of NPQ for the holiday candies, you get 2.487 approximately. But now my question to you, how do I combine them? How do I combine two independent standard deviations? Variance. Square them, add them, square root them back. So that's exactly what I'm going to do. Square them, add them, square root them back. Was it that one on the computer? Yay, I did it. That's what the computer, that's what my calculator says. All right, one more, because I have till 43. Bring this back with me. But yeah, that problem. See, the thing is, they don't tell you what is expected of you on the problem. It took me an extra couple of moments. Initially, I had thought I had to use my list to get this thing done. But then when my list came up with a standard deviation of 0, I was like, something's going on here. I went back and read the question, and then it clicked. I'm like, oh, snap. This is a binomial problem. And with a binomial problem, I have to use those formulas. But then I have to combine the two expected means and the two expected standard deviations. So, yes. That's why that answer was that one. Next. Last question. Oh, interesting. In a random sample of 60 shoppers chosen from the shoppers at a large mall, 36 indicated that they had been to a movie in the past month. Good for them. In an independent random sample of 50 shoppers chosen from the shoppers in a downtown shopping area, 31 indicated that they had been to a movie in the past month. I like the fact that they threw in the word independent. What significant tense should be used to determine whether these data provide sufficient evidence to reject the hypothesis or the null hypothesis that the proportion of shoppers at the mall who had been to a movie in the past month is the same as the proportion of shoppers in the downtown shopping area who had been to a movie in the past month? So, which test? Interesting. Obviously, it depends on if you have categorical data or quantitative data. Since you're not dealing with multiple categories, you're not going to be dealing with chi-squared, obviously. They're independent tests, which is nice. I'll leave it to you. We'll see what you pick. Ooh, chart view. I don't want to do chart view. I want to do other view. Can I do other view? Whoa! Oh, what did I do? Did I really click that? Crap. Hold on. I apologize. Will it actually go back? There it is. Cool. Oh, cool. So if you picked an answer, it still has the answer that you picked. I panicked for half a second. That's great. Cool. Well, you got to pick it very quickly because the bell is going to be ringing very, very soon. Probably in one more minute. So I do have to talk about this one very briefly. These are two independent samples. This is categorical data. Since you're going to be dealing with categorical data, you need to be dealing with some form of a z-test. Seems to me, well, I'm waiting for it. Oh, wait, no. You got to pick an answer. Did he close up? Caster, it says that you didn't pick. Yeah. Pick it. Ooh, it looks like it was split. I'm still waiting on him to pick, though, but it was split between two proportion z-test and two sample test for means. Two sample t-test for means. You got to pick it. The bell's going to ring. Did he not pick it? Right. It was supposed to. I'll end the question. Boom. All done. Hold on. It'll be green. It'll be green. Come on, be green. Yay! It was. I just wanted the computer to confirm it for me. I wanted it to turn green. Anyway, we'll pick up with more of this on Thursday. Yay! Thank you. You too. Oh, if you didn't leave a comment in the chat, please make sure they do. I'm going to sign off in a moment. Thank you. You too. See you guys. Bye-bye. You too. See ya. You too. See ya. Bye. Have a good one.